So in the last part of this lecture, we will be discussing about the hypergeometric probability distribution. So here it's actually an extension. We can consider it as an extension of your binomial probability distribution. So let's look at the formula first. So if we have n total number of elements in a certain population, and the number of successes or your desired outcome in that particular population is equal to r, and of course, again, as an extension of the binomial, the rest, or the non-success or the non-failure or the undesirable outcomes is of course n minus r. And then you conduct a trial or an experiment consisting of n number of trials. So that's technically your sample size. So let x be the number of that successes in your trial n. And n minus x is the number of failures of your trial. So as I said, this is you can consider it as the extension of your binomial distribution or the binomial experiment, such that again you have here your two outcomes, and basically you only have two outcomes, and that you have here multiple trials, independent trials, and the probability must be consistent. Now, the thing is the difference between calculating the probability in the binomial probability distribution with this hypergeometric probability distribution is that you will now consider the number of elements in the population and your successes in your population. So you now have a population and a sample. So the formula can now be considered as this one. So the combination of x in of your desired outcomes in your sample among the possible successes in your population times the failures, the combinations of your failures in the undesired outcomes in the population over the combination of your n samples in your population. So let's look at this example. So we have the Brown Manufacturing that makes auto parts. They are sold to auto dealers. So last week, the company shipped 25 auto parts to a dealer. Later, it was found that 5 out of these parts were defective. By the time the company manager contacted the dealer, 4 auto parts from that shipment have already been sold. So what's the probability that 3 of those 4 parts were good parts and 1 was defective? So here you have your population shown as the 25 parts, and the actually the undesired outcomes here is actually 5, and you have your sample size, which is 4. So we are looking at the probability of getting 3 good parts out of the 4 that were shipped. So looking at the solution, so we can say n is equal to 25 and r is 20. So where does that 20 come from? So out of the 25, we can say that the success, the good parts, are the rest of the remaining 20. So we have 5 failed or defective parts, and out of 25, and then the rest, which is 20, are the good parts. So that's your desired outcome, the r, the good parts in the total population. And now you have, of course, is the defectives, and you sampled from the population, sampled 4. So what's the probability of getting 3? That's your x, 3 good parts and 1 bad part. So basically that's hypergeometric distribution. You just plug it in your equation and you will get a probability of 0.45, so less than a half. The probability of getting 3 out of 4 of the parts that were sampled from your population being good parts. So the probability that 3 of the 4 parts sold are good and 1 is effective is 0.45. So let's look at another example. Dawn Corporation has 12 employees who hold managerial positions. Of them, 7 are females and 5 are males. The company is planning to send 3 of these 12 managers to a conference. So if 3 managers are randomly selected out of 12, what is the probability that all 3 of them are female? And what's the probability that at most 1 of them is female? So let's look here at our population. Our population has basically 12 employees with managerial populations. So one outcome is 7, the other outcome is 5. So if you're going to select 3 out of the 12, so this is your population and this is your sample, 3. So what is the probability that all of them are female, or what's the probability that at most one of them is a female? So here you get your population size 12, you get the number of females, which is 7. 7 females, and then males are 5, of course, the other outcome. And then you get 3 samples, 3 personals from those 12. And well, you want all of them to be females, so of course x is also 3. So, and then of course n of x equal to 0. So plug it in the equation, you get a probability that all 3 managers selected is female is 0.1591. And for letter B, again, the same values. However, out of the x sample, x is 0 and x is 1. So here we are going to calculate 2 marginal probabilities, and the union of these marginal probabilities, where probability of not getting a woman and a probability of getting 1 woman out of the 3. Here is 0.0455, where it's an all-male group, or this is a 2 male, 1 female group. So you just add them. That's the probability of getting at most 1 person. So when you solve problems like these in statistics, you must first carefully comprehend the problem at hand. Because otherwise, statistics is fairly easy because you just plug in the equations. However, knowing the values to plug in your equations is integral, especially in statistics. How well you understand the question and what values you should use in plugging in in the equation. So here is the probability of at most. So you get either 0 or 1 female in your 3-person team. So this is first get a marginal probability of getting no female and marginal probability of getting 1 female, and then add them because at most the issue is at most. So you have the union of the 2 probabilities. So let's look now at Poisson probability distribution. So we have here your table of probability distribution. So what are the conditions to apply the Poisson probability distribution? How will we know that we will be using Poisson probability? So we have 3 conditions. So first is that x is a discrete random variable. Your occurrences are random and the occurrences are independent of each other. So unlike the binomial probability, there is no limit to the number of outcomes, and the probabilities is not necessarily consistent or constant. So here's an example. The number of accidents that occur on a given highway during a 1-week period, the number of customers entering a grocery store during a 1-hour interval, the number of television sets sold at a department store during a given week. So those are examples of Poisson probability where we can apply them. So according to the Poisson probability distribution, the probability of x occurrences on a certain interval is given by this equation, where you have your lambda as the mean number of occurrences in an interval and the value, the natural logarithm e. Okay, so this is your equation for the Poisson probability distribution. For your exams, it will be, I won't restrict you from using equation, so just write it in a index card for easy use. So anyway, so on average, so let's look at this example. So on average, a household receives 9.5 telemarketing phone calls per week. Using the Poisson distribution formula, find the probability that a randomly selected household receives exactly 6 telemarketing phone calls during a given week. So we have here, actually here's now the answer. But let's look at this problem. You have 9.5 phone calls per week and you want at x. So from our equations, the mean number of occurrences is the lambda. So this is the mu, or rather the average, the value for the average in the probability distribution. So 9.5 on average per week. So what's the probability that 6, our x, at 6 instances, you will have, or rather, a certain randomly selected household receives exactly 6 phone calls during that certain week. So you just plug in the formula, lambda is 9.5, and at 6 instances, which is our x. So you just plug it in and you will get a 0.0764 value. So it's a very, very small value. That's how rare it is to get uh, for your number or your household to get, say, telemarketing calls 6 times a week. You get at every phone call of the telemarketing, or rather, since the telemarketer calls 9.5 times on average among all households, so you will get 6 out of those 9.5. So that's the probability. So let's have another example. So a washing machine in a laundromat breaks down an average of 3 times per month. So using the Poisson probability distribution formula, find the probability that during the next month, this machine will have exactly 2 breakdowns or at most 1 breakdown. So the second question is again a type of a union probability. So you just add the marginal probabilities included in the term at most 1. So at exactly 2 breakdowns, so x is 2. So you have here the number of average breakdowns per month is 3. So lambda is 3. So just plug it in the equation, you will get 0.224. If it's at most 1 breakdown, that's the marginal probabilities involved here are no breakdowns or 1 breakdown. So for no breakdowns, it's 0.9092. And actually it's 0.0498, and then at 1 breakdown 0.1494. So the total or the union is 0.1992. So for easier calculations, we actually have tables of probabilities. The reason why we usually have tables of probabilities in our distribution, rather especially in the discrete distribution, is because it's a discrete distribution. So it's not continuous. You have fixed or discrete values. Anyway, so let's say for example here, on average, two new accounts are opened per day at an Imperial Savings Bank branch. Using the table in Appendix B, find, this is from our book, find the probability that on a given day, the number of new accounts opened at this bank will be exactly 6, at most 3, or at least 7. So from the table, you get the number of outcomes you have, and this is the lambda. So this is the average. So the average is 2.0. Just and then out of 6, at exactly 6, the probability is 0.0120. So that's the probability that on a certain given day, the number of new accounts is exactly 6. That's 0.012. Now, for the other one, at most 3. So that includes no accounts opened, 1 account opened, 2 accounts opened, or 3 accounts opened. So you just add the probabilities from the table. So if we look back at our table, 1.353, 1, 2, and 3. So at most 3. So you add all of this. And then at least 7. So you have here, what are the values involved here is 7, 8, or 9 accounts. Okay, another example. An auto salesperson sells an average of 0.9 car per day. So let X be the number of cars sold by the salesperson on any given day. So using the Poisson probability distribution table, write the probability distribution of your X and the graph. So this is your probability distribution of your X. This is actually lifted from the table. And this is your graph. This is the histogram of your probability distribution table. So in this last part of this lecture, we will look at mean and standard deviation of the Poisson probability distribution. So the mean of the Poisson probability distribution is equal to lambda, which is basically the on average value provided. And the standard deviation is actually square root of the lambda. So let's look at this example. An auto salesperson sells an average of 0.9 cars per day. So let X be the number of cars sold by the salesperson on any given day. Find the mean, variance, and standard deviation. So for the mean, you just get the value of lambda, which is 0.9. And for the standard deviation, the square root of this one is square root of 0.9 is not 0.003, it's 0.949 cars. So copyright to our reference book. So copyright John Wiley and Sons for these lecture slides.